we're going to continue to look at the atomic model and how it's developed over time. Where we're going to look now is how the electrons were determined where their placement was. So looking at the properties of light, first we know that all light is called electromagnetic radiation, and that it travels through space as waves, and the speed of light is 3 times 10 to the 8th meters per second. The electromagnetic spectrum, going from shortest wavelength to the longest wavelength, gamma rays, X-rays, UV, visible light, this is Roy G. Biv, the rainbow, infrared, microwaves, radio waves. The wavelength is the distance between corresponding points on adjacent waves. So if you've got a wave and you go from one point to the same point on the next wave, then that is its wavelength. The frequency is then how many times that wave passes, or how many waves pass a given point in 1 second. You'll see this written as 1 over s, or s to the -1. Waves per second is also called hertz. So we will be using 1 over s, or 1 to the -s most of the time, but that is also known as hertz. So when you see that, when you see hertz somewhere, you know what that's talking about. The formula to find the speed of light is wavelength times frequency, because they are both multiplied together to get speed, and speed of light is a constant, the 3.0 times 10 to the -8, then the two will just change inversely of each other, so that when they are multiplied, they will still get the speed of light. So if we use our formula, the speed of light formula is wavelength times frequency, and if we use that to determine the frequency of a wavelength that we're given, then we can use the formula. So it says find the frequency of radiation if the wavelength is 5.0 times 10 to the -8. So I know my wavelength is 5.0 times 10 to the -8 meters, and I know my constant, the speed of light, which is 3.0 times 10 to the 8th meters per second, then I can determine my unknown, my frequency, by plugging them into the formula. So I have 3.0 times 10 to the 8th meters per second equals the wavelength, 5.0 times 10 to the -8 meters times our unknown, the frequency. So to get our unknown, the frequency, by itself, we divide both sides of the equation by the wavelength, 5.0 times 10 to the -8 meters. These cancel out. Here, the meters will cancel out, and we'll be left with just per seconds, and that'll tell us how many waves per second. And this will give us then 6.0 times 10 to the 15th waves per second. The photoelectric effect. The photoelectric effect is how we are using solar power. We're harnessing those moving electrons, and we're able to use it as electricity. So what's going on is when you have metals and light shines on them, their electrons are excited and they remove themselves from the atoms, and then you have then another material that will capture the electrons and funnel them down into stored electricity. So just to get this to happen so we can capture it, you have to have a wave that's at a specific frequency. And if it's not above that frequency, then nothing will happen. But as long as it's above that frequency, then when the light hits the metal, that will cause the electrons to be emitted. Next, Planck. Max Planck is the one who was working with the waves of light and metals and finding this out. As he did, he came up with an energy formula to determine how much energy is in that wave. So the minimum amount of energy that can be lost or gained by an atom is called a quantum. Then our energy formula that Planck came up with is that energy is equal to the Planck's constant. That's that minimum amount of energy, that quantum, that can be released or absorbed by an atom, and you multiply that by the frequency. So if you know each wave is going to give this amount of energy, then multiply that by how many waves come per second, and you'll be able to determine then how much energy that wave has. Albert Einstein was also working with this, and since it was working with it as with light, he called it a photon versus just calling it a quantum amount of energy. So a photon is a quantum amount of light energy. We can also use that formula to determine how much energy a wave has. So in our example here, it says find the energy of radiation if the frequency is 6.15 times 10 to the 12th waves per second. So we take the energy formula, which equals Planck's constant times frequency, and Planck's constant equals Planck's constant is 6.626 times 10 to the negative 34 joules seconds. Then our frequency is 6.15 times 10 to the 12th waves per second. So we multiply these two numbers together. And we end up finding that the amount of energy is 4.07 times 10 to the negative 21st, and that's joules. seconds cancel out, and this is how much energy we have. Einstein and Bohr were working with hydrogen and looking at the spectrum of elements. They felt that that if an electron was just electricity, then our light energy must have something to do with the electrons. They first believed that it was the number of electrons that would determine how many wavelengths of color were given off from an element, but they soon found out that it was the movement of the electrons in the atom itself, not just the number that was determining its colors that it gave off. So when we look at where the placement of the electrons are, we have ground state. So this is when it's at its lowest point of energy. And we have excited state when it's at its highest point, meaning that some of those photons have hit that atom and the electrons have gained the energy and they're moving out to an excited state. So an energy level that's further out based on how much energy it has. So they're called energy levels where the electrons are found. So the more energy, the further away they're able to get from that positively charged nucleus. What happens is when you have an atom, so here's the nucleus, here's the energy levels out here, and I have an electron that's out here in an excited state. So it's had light shining on it, something that's gained energy, and then it falls back to the ground state. When it goes from excited state to ground state, it has to lose energy. And we know we do not create or destroy energy. It's simply moved and transferred from one type to another. So what happens here is then the energy is released as a wave, and that wave is what our eyes detect as a certain color. Now, they started with hydrogen because remember, they first thought that it had to do with what color it was, had to do with how many electrons it had. So they started with hydrogen because hydrogen, first element on the periodic table, it has one proton and one electron. So they felt when they pass the light through a prism and it separates into the different colors, there's only going to be one color because there's only one electron. When they passed it through the prism, they actually found out that there were 4 different colors. And so their hypothesis about the number of electrons determining the color was not exactly correct. And that's what led them to come up with then what's called the planetary model, with electrons orbiting the nucleus. So you might remember these from freshman year. A Bohr model is simply one that shows the energy levels and the placement of the electrons. So it always shows then like the number, well, what's in the nucleus. So if we look at a nitrogen atom, then we know that there are 7 protons in the nucleus. This particular atom has 7 neutrons in the nucleus. Then Bohr said each individual electron has its own orbit around the nucleus. We now know that that's a little different, that more than one electron can fit in a place because we're talking about a 3D structure, not two-dimensional. And 2 electrons can fit in that first space closest to the nucleus. And then the electrons have to go further out. And in the second one, they can hold a total of 8. But since we only need 7, we've got 2 electrons here. We're only going to have 5 more out here. And that's a Bohr model. And he called his model the planetary model. After this, then we have people who start working more on the mathematical side of it and trying to determine then how feasible everything was. And they were really focused on electrons being waves. There were some people that were focused on electrons being particles, but then there were some that thought, well, maybe that electrons were just waves of energy. Louis de Broglie, he was the one that was working with the waves were like electrons, the same type of properties electrons would have. Heisenberg was looking at the wave and the particle thing, and he was saying, well, if it is a particle and we're finding that particle by hitting it with energy to make it move, then we need to keep in mind that it is impossible to determine where the electron is and the path that it's going to take. You can't do both of those at the same time because you're using energy to cause the electron to move. So if you knew the electron was there, well, it's not there anymore because you just gave it energy and excited it and moved it to a different level. The next scientist that we see that comes up in the creation of the model of the atom is Schrodinger. And Schrodinger is basically, you've probably heard him referenced if you've ever watched Big Bang Theory or anything when they talk about Schrodinger's cat. Well, that's the same person that we're talking about. And he had a mathematical equation that helped set up where the possible locations of the electrons were. This model was called the quantum model. And we use this quantum number to locate things with everything that we do. For a quantum number, you're going to have 4 different portions of it. You're going to have the principal energy level, okay, what energy level it's in. Then you're going to have the angular momentum, or the shape of the orbital or sublevel that it's spinning around in. Then you're going to have the orientation, so where it is in that space. And then you're going to have its spin. The spin is just saying north or south. Now, if we look at the periodic table, the periodic table is arranged to help us see how the electrons fill up this quantum number. And a better way to think of your quantum number is if you think about like an airplane ticket or a concert ticket or anything like that. You're going to have a row number, or like, actually, I guess first we would have a section number. And then what row you're in, and then your seat number. This is a quantum number. It tells us what energy level we can find it in. It tells us then what sublevel it's located in and which particular place it's located. So this is a quantum number, just like when you get, so if you get, you know, like you're in section B, or I guess you'd be in section like 224, row L, and seat 9. Then I know I go to this section, I go to this row, and I go to the 9th seat, and that's where I'm going to sit. The quantum number is exactly like that, except for electrons. And our periodic table is very kind to be set up and organized so that we can follow these. So what we're going to do, if you've noticed, I've crossed out helium up here at the top, and I've moved it over here because we're just looking at the numbers as far as how many electrons they have. Helium is over here because of the family that it's in. It's this yellow column. It's like those. But all we're worried about right now is the number. So we're going to scoot that over to the other side. Now, we have our sublevels. We have S, P, D, and F. The S sublevel can hold 2 electrons. The P sublevel can hold 6 electrons. D can hold 10, and F can hold 14. And if you notice that when we look at our sublevels, then once the sublevel shows up in a particular place, then they will, every energy level from there on will have that. So if we look at the first energy level, has 1 sublevel, and it's an S. The second has 2 sublevels, and they're S and P. The third sublevel has 3, S, P, D. The fourth sublevel and everything below that has S, P, D, and F. It has all of them. So if we fill out this table, we say, okay, the first energy level has an S sublevel, and there's 1 orbital in it, and it can hold 2 electrons because 1 orbital can always hold 2 electrons. So since the first energy level has the S sublevel, then we know every other energy level that we would come to would also have an S. And an S, no matter what level, can only hold 2 electrons because it only has 1 orbital. The shape of an S is a sphere. So it's just, you know, just a sphere around the nucleus, and that's where 2 electrons can spin around. Then we said the second energy level has two sublevels, S and P. P has 3 orbitals and can hold a total of 6 electrons. And then since the second energy level has a P, that means every energy level past them will have a P sublevel with 3 orbitals that can hold 6 electrons. Then the third energy level also has a D sublevel that has 5 orbitals, so it can hold 10 electrons. So we know then every level past then is also going to have a D. Then the fourth energy level also has an F, which has 7 orbitals or can hold 14 electrons. Now, if we look at then, so for the energy level, the first energy level can hold a total of 2 electrons. The second energy level can hold a total of 8 electrons. The third can hold 18, and the fourth and fifth and so on can hold 32. We got these numbers by adding together the electrons that fit in the sublevel. So that tells us how many electrons can fit in the entire energy level. So an electron configuration is basically just telling exactly where you find all of the electrons for that particular element. There are some rules that we need to be aware of. We need to make sure that we know the off-bow principle, which says when electrons are starting to fill in an atom, they're always going to go to the smallest energy level first. So they're always going to go down to the first energy level closest to the nucleus and start filling there. The reason is because those positive protons are located in the nucleus, and that's what's attracting the negative electrons. There's a note here, and we'll look at this when we start actually doing some of them, and that's that the 4s is lower than the 3d, and I'll show you how you can see that on the periodic table also. The Pauli exclusion principle has to do with the spin of the electrons. We know that an orbital can hold 2 electrons. Well, Benjamin Franklin, way back in the day, told us that opposites attract and like charges repel. So how are we putting 2 negative particles so close together and they're spinning around? Well, it's because something about them is opposite, and it's their spin. One of them spinning north and one of them spinning south, so then they can occupy a space that's closer together. Hund's rule is, I like to call this the school bus rule, okay? It means that if there's more than one orbital in a sublevel, then each orbital will get an electron before any of the electrons pair up in an orbital. And the reason I call this a school bus rule is if you think about, football players and all their gear get on a school bus, they're going to sit 1 per seat. And then when all the seats are taken and they're forced to sit with somebody else, then they will begin to pair up. So it's exactly the same thing with our electrons. Our electrons will go 1 in each orbital, and then when all the orbitals have 1, they have to go back and put another one in there. So when we look at electron configuration, the notation or the actual writing of it tells us the energy level. That's denoted by the 1. It shows us the sublevel. That's denoted by the S. And then the 2. That tells me how many electrons are in that energy level's sublevel. And as I said, we will look at the periodic table and how we can use this as a guide. Okay, so if we look at our periodic table, they're divided up into periods, or what is called, or what's rows. So if we look at them, here's 1, 2, 3, 4, 5, 6, 7. There are 7 different rows on the periodic table. Those are our energy levels. So we know the first energy level has an S sublevel, and it can hold 2 electrons. After I put 2 electrons in that level, then there's nothing else there. So that means I have to go into the second energy level. The second energy level has an S sublevel that holds 2 electrons. Then after that, I go to the 2p sublevel, and it can hold 6 electrons. Once I've filled up that, then there's nowhere else to go, so I have to go to the third energy level, and it has an S, and it gets 2 electrons. And then the third energy level has a P, and it gets 6 electrons. And then there's nothing else there, so we have to go to the next one. Now, we talked about that the third energy level has 3 sublevels, SPD. Well, since the S sublevel is so small compared to this really monstrous D sublevel, the fourth energy level will actually fill up its S sublevel before the third energy level fills up its D sublevel. So, and that's just because this only needs 2 electrons in the 4s, and the 3d needs 10. So we're going to put 2 in the 4s, and then we fill up the 3d. After the 3d comes the 4p, and that holds 6. And then we go to the next one, and it just continues on. Now, when you fill up the S and the 4D and the 5P, then we come here and we do the 6S, and then there is where we have our F block that comes in. The F block can hold 14 electrons. It is so large that it will have to fill these up after the 6s. So the fifth energy level has already got electrons in its S and its P sublevels, and then the S gets 2 electrons in its S sublevel before the fourth one ever gets its any electrons in its F sublevel, because it's just so large and it takes so much energy to put electrons there. So if I'm going to do the electron configuration for hydrogen, then it would be 1s1, because it is the first element on the periodic table. So it has electrons in the first energy level, and in that sublevel S, there is 1 electron, and that's all the electrons hydrogen has. Helium has 2. So for helium, it's 1s2. Once we get past there, that's a total of 2 electrons. Well, lithium is element number 3. It has 3 electrons. So that means after the 1s, Then we start filling up the 2s, and it has 1. Then for oxygen, oxygen's going to be 1s2, 2s2, and 2p4 because it has a total of 8 electrons. So when we start filling them up, we have to fill the first energy level, its sublevel, and it gets 2 electrons. Then the second energy level, its S gets 2, and then its P gets 4. So 4 plus 2 plus 2 gives me a total of 8. And if you look at the periodic table, oxygen is element number 8. These are some more examples. So why don't you pause the video here, and then you can look at and check to see if you've done them correctly. Don't worry about it if you're having some trouble with this. We're going to work on this in class together. Now, to help show Pauli's exclusion principle, that one electron must spin north and one spin south, then we actually show a picture of the electron configuration. So hydrogen was 1s1, so for that one, we show 1s, we show the one orbital that the S sublevel has, and the fact that there's 1 electron. So I always put the up arrows first, but it doesn't matter if you would have put a down arrow. But it has 1 electron spinning in the 1 orbital that the S sublevel has in the first energy level. Lithium said has 3 electrons total. So 1s has 2, and the 2s has 1. Boron has 5, so 1s has 2, 2s has 2, and 2p, there are 3 orbitals, but only one of them has 1 electron to total 5 electrons. Nitrogen has 2 electrons in 1s, 2 and 2s, and then it has 3 in the 2p. So Hund's rule shows us that we have to have 1 electron in each orbital before they pair up, and Pauli's exclusion principle is the one that explains that they're spinning north and south. So this is basically a picture of the electron configuration of an element. You can abbreviate it by using the noble gases, which are the very last column on the periodic table. And you use that by simply putting the noble gas just before the element that you're going to use in brackets, and then you write its electron configuration. So we can do for bromine, so we don't have to draw 35, we don't have to put out where all 35 are. We show that it has the electron configuration just like argon, which takes us up to 18. And then here's where the other electrons are located. So pause this, do antimony, and see if you get it correct. Then you can do the same thing with the orbital diagramming. You can show the electrons the same way. So we don't have to draw 35 electrons. You can still just use the noble gas before it and then show how many electrons there are. Now, for the D block, the ones that where the S sublevel of the next energy level is filled prior to the D sublevel, there is an exception. It becomes very unstable whenever the 4s has 2 and then the D block is 1 away from being half filled. It becomes very unstable, and this electron here is pulled out by the D block, or by the D sublevel. It yanks it out and it puts it over there, because having both of these half filled makes it more stable than having the 4s filled and the D block being 1 away from half filled. The other place we see this is when there ends up being 9. The same thing happens. When the 4s is filled and then you end up with 9, so it's 1 away. Well, the same thing happens, and this electron is pulled out and it comes over here. So then this little bitty sublevel that can only hold 2 is half filled, and the one that can hold a total of 10 is completely filled. So sublevels which are filled or half filled are more stable than the other configurations, and that's what causes them to move.